Hi everyone, and welcome to The Sleepy Scientist. I'm really happy you're here. Tonight, we're going to go on a calm and quiet trip to learn something amazing. So get comfy, take a deep breath, and let's enjoy this peaceful science story together. Before we start, tell me in the comments, where are you watching from and what time is it for you right now? If you like relaxing science videos, don't forget to tap the like button. Now let's begin. Long before stars had names, before telescopes reached through time and glass to chart the heavens, the universe shimmered with questions. It was dark, but not empty. Quiet, but not silent. In that early hush, the first lights blinked into being like thoughts waking up inside the mind of space. They weren't bright at first, just soft pulses, whispers of heat and promise. These were the first stars, born from clouds of dust and gas that gathered like dreams too dense to stay asleep. Gravity, patient and persistent, curled around them, pulling the chaos into something more focused, more alive. And slowly, like kindling catching fire, the stars began to burn. To understand what happens when a star falls asleep, you must first know how it lives. A star is not a simple light in the sky. It is a furnace, a balancing act, a long, slow breath of fire held for billions of years. At its heart, hydrogen atoms crash into each other with such force that they fuse, becoming helium. In that act, a little bit of mass disappears, and in its place, energy, light, warmth. That's the secret a star holds in its core. It trades its own body for brilliance. It sacrifices matter for the sake of radiance. And it does this endlessly, peacefully, as long as it can. The star's life is a conversation between pressure and gravity. Gravity pulls everything inward, trying to crush the star under its own immense weight. But the heat from fusion pushes back, expanding outward, holding the collapse at bay. It is a quiet war, but neither side wins. Instead, they agree. A star exists in balance, not still, but steady. For millions, even billions of years, this equilibrium holds. The star glows. It warms nearby planets. It reaches across space to whisper to wandering comets and distant moons. It becomes a part of night's rhythm, part of our myths and calendars, our navigation and our prayers. But nothing lasts forever. Even the most faithful fire has limits. As the hydrogen in its core begins to run out, the star starts to change. It's subtle at first. A small stutter in its breath, a slight dimming or swelling. The fusion slows and gravity begins to win. The core contracts, and in that compression, it heats up again. For a while, the star may find new fuel, helium, carbon, heavier elements if it is massive enough. It flares brighter, grows larger, becomes something else entirely, a red giant, a supergiant. Its body expands even as its heart becomes denser and more desperate. This is not dying in the way we think of it. It is transformation. A star nearing the end of its life is not fading quietly into the background. It is writing its final poem in fire across the sky. The outer layers begin to peel away, pushed out by winds of light and heat. Shells of gas form around it like soft, glowing halos. The star is shedding its past, letting go of the matter it no longer needs. Some stars go gently, becoming planetary nebulae, soft, colourful clouds cradling a white-hot core. Others go violently, exploding in supernovae so bright they outshine entire galaxies. And in both, something new is made. Because this is the mystery that lives inside every star. It is both a beginning and an ending. Every atom in your body was once part of a star that fell asleep. The calcium in your teeth, the iron in your blood, the oxygen in your lungs, none of it could exist without stellar death. Stars do not disappear, they become. They leave behind white dwarfs, neutron stars, or even black holes. They scatter elements into the cosmos, seeding the clouds that will one day birth new stars, new planets, and perhaps new lives that will one day look up at the sky and wonder. But before we speak of death, we must pause in this moment, the moment just before, the quiet hour between being and not being, when the star still burns, but the burn is tired, when the balance still holds, but only barely. This is the moment when a star begins to fall asleep. It is not sudden, it is not loud, it is a slow closing of the eyes, a soft sigh into gravity's waiting arms. It remembers everything it has been, every orbit it warmed, every comet it touched, and as it begins to dim, It does not resist. It lets go. You can almost feel it, that surrender. A kind of cosmic trust. The star is not afraid. It has done its work. It has burned with purpose, held light where there was once only shadow. And now it returns to the dark, not as loss, but as gift. Even in sleep, a star gives. It gives its dust, its energy, its story. It gives birth to time itself, carved in light years and the echo of photons. To sleep for a star is not an end. It is a transformation wrapped in silence. The night sky holds thousands of these moments. When you look up, you're not just seeing stars, you are seeing memories. Some of them are already gone, their light still travelling, still telling their final chapters across the emptiness. Others are in the act of becoming. You are witnessing sleep in slow motion, the lullaby of the cosmos. And in that hush, you are part of the story too. You, made of stardust, shaped by time, lit by the same fusion that once powered suns. What happens when a star falls asleep? The universe listens, and in that listening something sacred unfolds. Now let's drift deeper into the place where sleep becomes silence and silence becomes shape. When a star uses up the last of its fuel, the quiet that follows is not simple absence, it is the beginning of something else. Depending on how massive the star once was, the story takes a new shape. For stars like our sun, the process is gentle, like a candle burning down to its final flicker. For the heavier stars, the giants, the titans, the end arrives with a brilliance so fierce it is almost impossible to describe. But either way, what remains is not nothing. It is memory, pressed into matter. Imagine the star's core, once bright and restless, now shrinking, pulling inwards like breath being held. If the star is small, this collapse will be stopped by pressure, an invisible hand that says, "This far and no farther." The atoms resist. Electrons push back and the core settles into a new form, a white dwarf. It is no longer burning, but it glows from the heat of everything it once was. A white dwarf is small, about the size of Earth, but it is unimaginably dense. A teaspoon of its matter would weigh tons. It no longer shines by fusing elements. It shines by remembering heat. It is the ember of a life once ablaze. But for larger stars, the collapse doesn't stop there. Gravity becomes greedy. It pulls the core tighter, past the strength of atoms, past the resistance of light. The star implodes in on itself, and in that sudden violence, the outer layers are thrown outward in a supernova. The explosion is not just destruction, it is creation. In that instant, temperatures soar and new elements are forged: gold, silver, uranium, the heavy things that planets and people are made of. These riches are not born in quiet, they are born in fire. They scatter into the universe, carried by shock waves that will ripple for centuries. At the centre of that chaos, something dense and strange remains. If the core is heavy enough, it becomes a neutron star, a city-sized object with the mass of the sun. Inside it, protons and electrons have fused into neutrons. It is a place where matter is so compressed that a single sugar cube of it would outweigh a mountain. Neutron stars spin rapidly, sending beams of radiation sweeping through space like lighthouses in the dark. Some of them pulse in rhythm, pulses ticking like the clocks of eternity. They are stars that no longer shine with fire, but still tell time. And yet some stars go even further. If the core is too massive, even neutrons cannot hold it up. There is no pressure strong enough, no resistance sturdy enough. The collapse continues endlessly, until it folds space itself. A black hole is born. It does not shine. It does not reflect. It is not a place but a boundary, an event horizon, beyond which nothing can return, not even light. It is the sleep that forgets waking, the silence so deep it becomes invisible. And yet black holes are not absence. They bend the fabric of space-time, influence the orbits of stars and galaxies, and possibly harbour the seeds of new beginnings. We often imagine black holes as devourers, swallowing all they touch. But that is only part of the story. They are also sculptors, shaping galaxies with their gravity. In the hearts of most galaxies, including our own Milky Way, lies a supermassive black hole. Around it, stars swirl like leaves in a whirlpool, held in elegant motion. These hidden giants may have helped form the structure of the universe itself, anchoring the luminous islands of stars we call home. They are not destroyers, they are keepers of momentum, a form of cosmic rhythm. So when a star falls asleep, it is not gone. It becomes part of something larger. It returns to the great cycle of matter and motion. Its ashes may drift through space for millions of years until they join a cloud, and that cloud collapses, and a new star is born. The light that once warmed a world may rise again, in another sky on another planet. Perhaps that light will grow grass or melt ice or help shape the eyes of creatures learning to see. Perhaps it will shine on oceans still learning to breathe. In this way, a star's death is also an offering. It gives the raw material for everything else. Even now you carry those gifts. The iron in your blood, the calcium in your bones, the carbon in every cell. These came from stars. You are not separate from the cosmos. You are its continuation, its echo in flesh. When you breathe, you are recycling stardust. When you look up at the night sky, the light you see may have been travelling for thousands of years, just to meet your eyes. And when those stars dim, when they finally sleep, they are not lost. They are written into you. In the quiet spaces between constellations, astronomers have found ghost light, soft glows from stars that have long since vanished. It drifts through galaxies like a memory, illuminating the past. Some galaxies shine more brightly than they should, not because of stars still burning, but because of stars that burned long ago. These lights, these echoes, are part of a cosmic afterlife, a way that stars linger, not as heat, but as story. Let's drift again, to the ancient star charts carved by hand, the stories of gods and creatures painted in the sky. Long before science, people saw the stars as living things, watchers, guides, storytellers. They did not know of white dwarfs or neutron stars or black holes, but they sensed that stars mattered, that their movements meant something, that their changes were worth noticing. Even then, in myth and ritual, we were trying to understand the language of light, and maybe they were right, in their own way. Stars do speak, not in words, but in patterns, in pulses and spectra, in gravitational waves and neutrino bursts. They tell us about time, about distance, about the chemistry of space. With every supernova we observe, we learn more about how galaxies grow, how planets form, how life might arise elsewhere. These events are not just endings, they are experiments conducted on a scale far beyond our reach, and we, small and curious, listen from afar. What happens when a star falls asleep? It changes the fabric of the universe. It sends out waves that ripple through everything. It leaves behind remnants that bend light, forge elements, mark time, and stir imagination. It teaches us that death is not disappearance but transition. That even in fading there is gift, that even in collapse there is creation. The sleep of a star is not something to fear, it is something to honour. It is the moment when energy becomes legacy, when fusion becomes memory, when light becomes the blueprint for all that follows. In that sense, the death of a star is the birth of 1,000 possibilities, a new planet, a new star, a new breath in a new life. Now, as we pause here, held in the gravity of wonder, let us listen to the silence a star leaves behind, not as emptiness, but as space to grow. You can almost hear it if you sit quietly enough, the hush that follows a star's final breath. Not a silence of loss, but a silence of return. In the universe, nothing is wasted. Even the end of a star is woven back into the fabric of space like thread being pulled gently into a larger tapestry. The star does not vanish. It becomes invisible in one form only to reappear in another, shaping the world in ways that outlive its light. The last light is not the end of seeing, it is the beginning of remembering. Imagine standing on a world orbiting a white dwarf. The star that once blazed above it now glows faintly, no longer alive with fusion but still warm with memory. The sky is quieter now, the days are dim but calm. Life here, if it exists, must be gentle, adapted to softness, slow to change. Yet even here life might bloom, warmed by the leftover heat of a long-forgotten sun. This quiet world is not lifeless. It is ancient, wrapped in the final chapters of stellar memory. What it lacks in brightness, it gains in depth. Somewhere else, around a neutron star, things are different. The star spins furiously, its gravity immense, its magnetic fields extreme. The remnants of its explosion still ripple through space, a reminder of how fiercely it once lived. It beams radio waves into the cosmos in perfect rhythm, like a heart that never stops. Time seems different here, measured not in hours or years, but in pulses, in gravity's distortions, in the tremble of light bent by mass. It is a world of extremes. But even here, planets have been found, strange, dark worlds orbiting the bones of a supernova. Life as we know it may not flourish in such places, but the possibility remains. Where there is gravity and time, there may be curiosity, and then there are the places we cannot see, around black holes, where light bends back on itself and time flows strangely. These are not voids, but boundaries, the edge of knowing. The event horizon is like a curtain drawn over the next act of the universe, hiding what happens beyond from even the fastest photons. Yet the black hole influences everything nearby. Stars orbit it, dust spirals in, light bends around it, and time slows. Perhaps inside something continues, or perhaps it ends. We do not know, but the mystery itself becomes a kind of beauty. These remnants, the dwarf, the neutron star, the black hole, are not just what remains after the last light. They are the carriers of stories. They shape galaxies. They anchor motion. They are the punctuation marks in the sentence of the cosmos. Some drift alone, others live in pairs, orbiting partners that pull at them, draw light from them, awaken brief flashes of activity in their otherwise sleeping hearts. Even in death, stars are not alone. They continue to interact, to move, to give. Now imagine the stardust blown into the arms of space. It drifts for years, cooled and carried by cosmic winds. Some of it will join a nebula, a vast, colourful cloud of gas and dust. These nebulae are more than beautiful, they are cradles. In their folds, new stars are born. Slowly, under the weight of gravity, knots of gas condense, warm and begin to glow. The cycle begins again. From death, new birth. From silence, new song. Every star is part of a long chain, each one a link forged by the last. Our own sun, gentle and yellow, will one day follow the same path. Not in our lifetimes, not in the lifetime of humanity, but someday. It will swell into a red giant, engulfing the inner planets, possibly even our Earth. Then it will shed its outer layers, forming a glowing shell, a planetary nebula, while the core shrinks into a white dwarf. The sun will no longer burn, but it will shine with the heat of what it once was, and for billions of years that white dwarf will cool, fading slowly until it is no longer visible. A black dwarf, a cold ember, a final whisper. But even then its elements will remain. Already the sun has made life possible. It powers photosynthesis. It stirs the winds and drives the tides. It allows us to see, to grow, to wonder. When it goes, it will have already given more than most stars ever do. And what it leaves behind, our bones, our breath, our stories, will carry its warmth forward. We are the sun's long echo. And someday the atoms in your hand may find themselves part of a new world warmed by a different star. And this is what it means to be made of stardust. Not just that we come from stars, but that we are part of their story. We inherit their endings and shape their continuations. The calcium in your teeth once pulsed in a dying red giant. The oxygen in your lungs once spun in the outer layers of a supernova. You are not apart from the stars. You are their memory made flesh, their light. Rewritten in blood and thought and time, even the universe itself remembers. The cosmic microwave background, the faint afterglow of the Big Bang still hums, quietly stretched by time, but not silenced. It is the oldest light we can see, the soft echo of the first fire. And beyond it, in the dark spaces, we are only beginning to understand more light waits. Perhaps from stars too far to reach. Perhaps from other universes entirely. We do not yet know, but we are listening. To watch a star fall asleep is to be reminded of patience. The universe moves slowly. It builds over eons. It destroys not with cruelty, but with transformation. And in those slow changes, something beautiful is always made. Light into life, life into thought, thought into wonder. We are witnesses. We are participants. We are small but not insignificant. So when you look up at night, let it be with quiet awe. Let it be with the knowledge that every twinkle is a conversation between time and fire. That some stars you see are already gone, but their light is still arriving, still telling their story, that every constellation is a map of memory, that every space between the stars is filled with what once was and what may yet be. And if one night you see a star fade, a nova, a supernova, a sudden change, know that you have seen something rare, a heartbeat ending, a light returning, a gift being passed along to the future. That star has fallen asleep. But its sleep will awaken something new. This is the gentle secret the universe keeps. Nothing truly ends. It simply becomes. There is a weight in the universe that cannot be seen, only felt. It pulls without hands, bends without touching, and shapes the future of stars with a force so patient it takes millions of years to finish a single sentence. This is gravity, not the kind that makes apples fall or feet stay grounded, but the kind that writes the fate of stars. It is the gravity of goodbye, the quiet force that draws the final curtain on the life of a sun. To understand how stars collapse into darkness, you must first know that gravity is not a destroyer. It is a sculptor. It carves the ending with care. A star is a story told in balance. From the moment it is born in a cradle of dust and fire, gravity begins its pull. It gathers atoms together, squeezes gas clouds tighter, until the pressure in the center becomes unbearable. Heat rises, hydrogen fuses. A star is born not in silence but in struggle. And from that first ignition, it fights back. Heat pushes outward, gravity pulls inward, and between these two a delicate agreement is formed. That agreement is called equilibrium, and it is the breath of a star. But a star's fuel is not infinite. It burns hydrogen into helium, and for a long time, sometimes billions of years, that is enough. But when the core begins to run out of hydrogen, the balance tips. Gravity, patient all along, begins to win. The core contracts, the outer layers expand. The star grows larger, redder, colder on the outside but hotter within. It becomes a red giant. If the star is large enough, this is just the beginning. New layers of fusion begin, helium into carbon, carbon into oxygen, and onward to heavier elements, each step shorter, faster, more desperate than the last. The weight at the center of a massive star grows unbearable. The fusion creates iron, but iron is the end of the line. It does not give energy when it fuses, it takes it. And so in a moment, the core can no longer hold. The pressure drops, gravity rushes in. The core collapses faster than thought, faster than light can escape. In less than a second, the center of the star is crushed, and the outer layers, sensing the void, crash inward too. The result is a rebound, a shockwave fierce and hot blasting the star apart in a supernova. For a brief time, the dying star shines brighter than an entire galaxy. In that light is sorrow and gift. The explosion spreads heavy elements into space, gold, uranium, nickel, elements that only exist because of death. The universe is richer for this violence. But at the center, in the place where the star once lived, something new has formed. The core, compressed beyond belief, has become a neutron star. Or, if the collapse is too complete, too deep, too final, it becomes a black hole. A neutron star is a paradox. It is the remnant of a death, yet it spins with impossible energy. It is only about 20 kilometers wide, yet more massive than our Sun. Inside, atoms are stripped of their structure. Protons and electrons are fused into neutrons. It is a single atomic nucleus stretched across the size of a city. It is dense beyond comprehension, so dense that a spoonful of it would outweigh mountains. And yet it moves. It spins. Some neutron stars, called pulsars, emit beams of radiation that sweep the sky like cosmic lighthouses. Each spin is a memory of the star that was, each pulse a beat in the dark. But gravity does not always stop at a neutron star. When the original star is massive enough, at least 20 or 30 times the mass of the Sun, its core collapses with such intensity that not even neutrons can resist. The matter collapses into a single point, a singularity, where all known laws of physics break down. Surrounding it is the event horizon, the boundary beyond which nothing escapes, not even light. This is a black hole, and though it cannot be seen directly, its presence is known. Light bends around it, stars orbit it, time slows near it, space itself curves in its presence. The formation of a black hole is not a violent explosion, but a quiet folding. The star falls inward forever, crushed by its own mass, until it disappears behind its own gravity. From outside, the process appears slow. A distant observer sees the collapse freeze at the horizon, time stretching infinitely. But from the star's own frame, the fall is quick, final, total. And yet, even in this collapse, there is creation. Black holes anchor galaxies. They shape the paths of stars. They gather matter and energy in spirals of motion, glowing hot with friction and magnetism before being consumed. The gravity of goodbye is not cruel, it is inevitable. It is what happens when the fire is gone and only the weight remains. But it is not without beauty. In collapse there is transformation. In the last breath of a star there is the birth of a new cosmic structure. These remnants do not glow like suns, but they tell time, they shape space, they whisper through gravitational waves that ripple across the universe, passing through planets and stars, even through you without a sound. Imagine that, being touched by the silent tremor of a star collapsing halfway across the universe. Detectors on Earth, delicate as spiderwebs, have felt these waves. They come from neutron stars merging, from black holes dancing into one another, from goodbyes written in gravity, and we, small and listening, have heard them. For the first time in history we have caught the echoes of stellar collapse, not in light, but in the stretch and curve of space-time itself. So when a star collapses into darkness, it does not leave nothing behind. It leaves weight, it leaves structure, it leaves a message written in the curve of space and the rhythm of orbits. It is not the end of influence, only the end of light. Its goodbye is not a silence. It is a shift, a ripple, a memory that cannot be erased. And we, made of stardust, feel that shift. We are born in the dust of Dieu's supernovae. We move through gravity wells left by stars long gone. We orbit a sun that will one day write its own goodbye. And in that knowledge is wonder, not fear but reverence. The universe is not static. It breathes in fire and exhales form. It loses stars and gains depth. It collapses and expands, folds and unfolds, like lungs filled with stars. This is the beginning of understanding how stars fall into darkness. Not with violence alone, but with weight. Not as endings, but as transitions. The gravity of goodbye is not the end of the story. It is the turning of a page. Let's drift deeper now into the silence that follows collapse. For a star, the end is never truly an end. It is a change in state, a reconfiguration of matter, a redrawing of cosmic identity. When light fades, form remains. What once gave warmth now gives weight. What once burned now bends. And this new identity, the neutron star or black hole, is not merely a grave but a new presence. One that influences space and time in ways we are only beginning to understand. A neutron star does not die quietly. Though it no longer fuses elements in its core, it is alive in its own way. It spins, faster than any planet, faster than any dancer. Some spin dozens of times per second, others hundreds. Imagine a star heavier than the sun compressed into a sphere the size of a city block, rotating 30 or 40 times in the time it takes you to blink. That speed is a legacy of the star's former size. As it shrinks, it preserves its angular momentum, becoming a cosmic top that never wobbles, never rests. Its spin sends beams of electromagnetic radiation into the universe, flashing pulses of light, like a heartbeat we can measure from across galaxies. These stars are known as pulsars. Their beams sweep the cosmos like lighthouses in the dark. And we, here on Earth, have been listening. Radio telescopes pick up their signals like ticking clocks in the silence of space. Each pulse tells a story not just of the star itself, but of what surrounds it. As the beam bends through space, it reveals the warping of gravity. As it flickers through interstellar dust, it teaches us about the matter drifting between stars. Pulsars are not relics, they are observatories, measuring tools, memories that still move. Some neutron stars are not alone, they orbit other stars. They pull from them, they feed. In binary systems, a neutron star may draw gas from a companion. This gas spirals in, forming an accretion disk, a glowing ring of matter spinning faster and faster as it falls inward. The disk glows in X-rays, hot and furious, revealing violent physics and magnetic storms. Sometimes this transfer of matter becomes unstable, and the system flares, a sudden brightening, a scream across the electromagnetic spectrum. These moments remind us that the dead are not silent, that even collapsed stars have appetites, and in feeding they flash with life again. And when two neutron stars meet, when they spiral inward, pulled together by the very gravity that once ended their lives, they collide. This collision, called a kilonova, is among the most powerful events in the universe. For a brief moment, the explosion creates gold and platinum, rare elements forged in fusion too fast to last. It sends gravitational waves rippling outward, stretching space-time itself. We have detected these waves, tiny distortions in the fabric of reality, travelling at the speed of light, whispering of titanic events in distant skies. They arrive here, passing through you and me, imperceptible yet real. The collision may result in a heavier neutron star, or if too massive, the final step, the birth of a black hole, a place where gravity folds inward completely, where the escape velocity exceeds the speed of light, where time and space twist into a spiral that ends in a point of no return. Black holes do not glow, they do not reflect, yet they are not invisible. They leave footprints in the motion of nearby stars. They leave fingerprints in X-rays emitted from falling gas. They cast shadows when backlit by galaxies, as captured by the Event Horizon telescope. That shadow, first seen in 2019, was the outline of absence, the shape of gravity alone. Black holes are not simply holes. They are regions where matter has been compressed into infinite density. The edge, the event horizon, is not a surface but a threshold. From the outside, time slows as you approach it. To a distant observer, nothing ever fully crosses. The star that collapsed appears frozen at the edge, dimming slowly, red-shifting into nothing. But from the viewpoint of the infalling matter, the fall is swift and final. Inside, space and time no longer behave as we understand them. They curve, fold, perhaps even connect to somewhere else. Some theories suggest wormholes, others the seeds of new universes. We do not yet know, we can only imagine, and yet even the darkest places give off clues. Hawking radiation, named for physicist Stephen Hawking, is the theoretical process by which black holes slowly evaporate over unimaginable timescales. Quantum particles flicker into existence at the edge, with one falling in and one escaping. The escaping particle steals a bit of the black hole's mass. Over trillions of years it may shrink, dim, vanish. The most massive giants of today may someday fade to whispers of mass, then to memory. Even gravity can let go, eventually. But long before then, black holes will shape the cosmos. They reside in the centres of galaxies. Some are millions, even billions of times more massive than the Sun. These supermassive black holes act as anchors, gathering stars into swirling disks, fueling the heart of spiral arms. Galaxies grow and dance around them, like leaves around a whirlpool. When they feed, they blaze. The falling gas lights up as quasars, the brightest beacons in the sky. These are not the end of stars, they are the heartbeats of galaxies. The gravity of goodbye, then, is not just an end, it is a transformation. It is the moment when fusion surrenders to collapse, when light bows to weight, and when matter becomes geometry. A collapsed star may no longer burn, but it shapes orbits. It sculpts time, it creates waves that hum through space long after light is gone. And in those waves, we learn. We learn not just about stars, but about ourselves. We learn that even in our smallest particles, our iron and oxygen, our calcium and carbon, we carry the memory of death and rebirth. We are built from the gravity of goodbye. Our bodies carry the ashes of collapsed stars. Our world orbits a sun that is temporary. And yet, in that temporariness, there is meaning. Every ending in space is a chance for rearrangement. Every collapse holds the potential for renewal. When you lie beneath the stars and feel their light on your skin, know that you are receiving messages from across time. Some of those stars may already be gone. Some may be nearing their own goodbye. Some may be collapsing even now, their final light already on its way. You are a witness to an unfolding that takes millions of years. You are part of the story that gravity tells. The rise, the balance, the fall. And in that story nothing is lost. Matter becomes form. Form becomes influence. Influence becomes wave, and wave becomes understanding. The universe does not throw anything away. It transforms, it bends, it remembers. So when a star collapses into darkness, it is not erasure. It is not absence. It is the gravity of goodbye, the soft pull toward what comes next. Let us drift now into the final silence, the place where collapse has already happened, and only the echo of form remains. Here, in the aftermath of stellar death, the universe begins to reshape what's left. The collapsed star no longer shines, no longer burns with the fury of fusion. And yet, in its darkness, it leaves behind fingerprints on the dust that gathers, the light that bends, the galaxies that turn. It is the gravity of goodbye that holds it all together, long after the fire is gone. Consider a white dwarf, once the quiet core of a sun-like star. It no longer fuses, no longer fights gravity with heat. It is simply there, dense, dim, cooling. For billions of years, it will sit at the center of a planetary nebula, glowing faintly from residual heat, slowly fading. There is no explosion here, no flash, just a long exhale, a soft, glowing ember in the dark. And in its stillness, it teaches us something profound, that not all goodbyes are loud. Some are slow, graceful, like twilight slipping into night. Eventually, even the white dwarf cools beyond light. It becomes a black dwarf, a theoretical object so old we've never seen one. The universe simply isn't old enough yet. But in time, all white dwarfs may fade into these dark remnants. Cold, silent, still holding the weight of what they once were. Even without light, they will drift through space, circling galactic centers, shaping paths with gravity alone. Their farewell is permanent, yet peaceful, a return to quiet. Elsewhere, neutron stars spin on. Over millions of years, their magnetic fields weaken, their energy drains, and they, too, begin to fade. The pulses that once swept space slow and stop. No more beams, no more clocks ticking across the cosmos. What remains is a sphere of frozen neutrons, still dense, still strange, but quiet now. The beat has ended. And in that hush, the universe moves on. The black holes remain longer. Perhaps forever. In their silence, they gather mass. Dust, gas, stars too close. Everything falls in. Some black holes may grow to monstrous size, consuming suns, shaping star systems. But they do not do this with rage. There is no hunger in their gravity, only inevitability. Objects fall toward them because space itself curves in their direction. It is the shape of the universe that makes falling necessary. And yet there may come a time when even black holes begin to die. Slowly, silently, through hawking radiation. Particle by particle they release themselves. Not in heat, not in waves, but in the quietest kind of release. It may take a trillion years, but eventually even the black holes may vanish. The universe may grow cold, dark, thin. The stars will all be gone. The galaxies stretched apart by expansion. The fabric of space-time grown quiet. But that is not the end, because in every transformation something is passed forward. The stars may fade, but their elements will remain. The hydrogen they forged into helium, the iron they left behind in supernovae, the carbon they gave to comets and dust, these linger. They form planets, they form oceans, they form life. Every breath you take contains atoms that passed through stars long ago. Every heartbeat is made possible by the calcium once crushed in ancient cores. You are living proof that goodbyes are not losses, they are legacies. Think of Earth itself floating in this vastness. Our planet circles a star not yet ready to say goodbye. But it will someday. The sun will swell, it will change, and Earth, or what remains of it, will bear witness to that farewell. But long before that, we have already been shaped by goodbyes. The gold in your ring, the oxygen in your lungs, the phosphorus in your bones, these came from stars that collapsed into silence. You are in every sense a descendant of their endings. And even now, across the sky, telescopes peer into those distant deaths. We see supernova remnants, gas clouds shaped like petals, glowing with the memory of light. We see black holes tugging on starlight, stretching it into arcs. We see neutron stars spinning, pulsing, dancing in pairs before merging. These are not just facts. They are lullabies written in radiation, poems carved in the curve of space-time, messages sent across eternity, not in words but in gravity. When we study these collapses, we are not just looking at endings, we are tracing the movement of time. Every gravitational wave that passes through us is a soft drumbeat from the heart of the cosmos. Every element we find in meteorites is a relic of fire and fall. Every map of the stars is a record of change. And yet through it all, the universe feels calm. It does not hurry, it does not mourn, and it accepts the fading of light as naturally as it accepts the rise. It gives space for endings. It welcomes transformation, and in doing so it teaches us to see beauty in what leaves, as much as in what arrives. We, with our brief lifespans and urgent clocks, often fear goodbyes. We think of them as losses, but the universe does not lose. It recycles, it reshapes, it remembers. The star that collapses is not gone. It is folded into the next act. Its gravity still sings, its story still echoes, its matter still moves. And if we listen quietly, we can feel it. So let your gaze rise to the sky again. Look for the stars that flicker, for the nebulas that bloom, for the curves of galaxies held by hidden giants. Know that every light you see is temporary, that every mass you feel is borrowed, that every goodbye you witness is a step in the great unfolding. The gravity of goodbye is not the closing of a door, it is the turning of the wheel. It is the soft voice that says, now begin something new. Even the darkest collapse, even the final silence of a star becomes part of the next chapter. That is how the universe writes its story, not in permanence, but in motion. And we, made of those same atoms, feel the pull too. We live, we change, we say goodbye, and in doing so we continue the dance of matter and time. The stars may fall, their light may fade, but their gravity remains. And in that pull, something eternal's held. There is a kind of fire that doesn't burn, not in the way we know it. It does not dance with flame or flicker in the wind. It glows, but without smoke. It heats, but without flame. This is the fire that lingers after a star dies. A silent fire, soft and enduring, cradled in the remnants of what once burned bright. It is the warmth of memory in the cosmos, the slow cooling of a life that once gave light. And though we often speak of stars in terms of birth and death, there is something quiet and remarkable that happens after, the long, unhurried twilight of their existence. When a star like our sun exhausts its fuel, it doesn't explode. It expands into a red giant, gently swelling to swallow its nearest planets, its outer layers stretching thin, glowing with a pale, dying light. Eventually those outer layers peel away entirely, floating into space to form a planetary nebula, a delicate cloud of colour and gas, shaped by winds of light and time. At the centre of this slow unravelling storm remains the core of the star. What's left is a white dwarf, and here begins the quietest chapter of all. A white dwarf is not truly dead. It no longer fuses elements, no longer generates light from within, but it glows. It glows with the leftover heat of its past. Compressed into a sphere no larger than Earth, yet with nearly the mass of the Sun, it is unimaginably dense. A spoonful of it would weigh as much as a small mountain. Its atoms are packed so tightly that electrons, normally floating freely around their nuclei, are pressed into a state of constant resistance. This pressure, called electron degeneracy pressure, keeps the star from collapsing further. It is gravity held in tension by quantum law. For billions of years, this white dwarf will slowly cool, radiating its heat into space. No more fusion occurs, no new light is made. But the glow remains, a kind of cosmic afterglow, a warm whisper from the past. It is a reminder that even when the fires of fusion go out, something can still shine. A white dwarf is the ember of a star's soul, drifting quietly in the dark. And though it has ceased all active creation, it is not without influence. Its mass continues to curve space. Its presence still holds gravity's touch. Around some white dwarfs, planets continue to orbit. These are the survivors, worlds that escape the engulfing grasp of the red giant phase. And they are often scarred by the past. Some bear evidence of atmospheres lost. Others are pierced by metallic cores stripped bare. In some systems, new debris disks form from the remnants of shattered planets or captured asteroids, swirling in slow, dusty rings around the quiet star. These structures hint at a strange kind of rebirth, not of the star but of the system it once ruled. Sometimes these white dwarfs find themselves in the company of another star. In a binary system where a white dwarf orbits a companion, new drama can unfold. If the companion star is close enough, matter from it may begin to drift onto the white dwarf's surface. At first, this is subtle, hydrogen falling gently, building up like a fine mist. But as the pressure increases, the surface of the white dwarf can ignite in a thermonuclear flash, a nova. This sudden release of energy lights up the sky with a burst of renewed brightness, a brief echo of the fire that once defined it. And in rarer cases, the white dwarf collects too much. The falling mass tips it past a critical threshold, the Chandrasekhar limit, and the star can no longer support its own weight. Gravity wins completely. The white dwarf collapses and explodes in a Type Ia supernova, a brilliant, catastrophic end. These explosions are used by astronomers to measure the expansion of the universe because they shine with such consistent intensity. So even in its death, the white dwarf becomes a guidepost, a signal, a tool by which we map the great distances of space. But most white dwarfs avoid this fate. They remain stable, glowing faintly, cooling slowly. Over time, they darken, becoming invisible to the eye. Eventually, they may reach a state of complete darkness, a black dwarf. No light, no heat, only mass and memory. These black dwarfs are theoretical, as the universe is not yet old enough for any white dwarf to have cooled so completely. But one day, in a far future where the stars are gone and galaxies have dimmed, the cosmos may be filled with them. Silent, motionless echoes of stars that once breathed light. And yet, even in this cold and quiet end, there is story. These remnants may wander through space, passing close to other systems, stirring orbits, disturbing comets, seeding new paths. Some may fall into black holes, others may collide with one another. Even in their apparent stillness, they remain players in the cosmic symphony. Their silence is not emptiness, it is potential stored in stillness. It is comforting, in a way, to know that stars do not vanish. They become something else. Even after death, they continue to shape the universe. Their dust becomes the soil of new worlds. Their remnants bend the paths of planets. Their stories are written into the curves of space-time. And we, made from their elements, carry that legacy. We are, each of us, a fragment of silent fire, our atoms once warmed by distant suns, our bodies echoing with the long cold glow of stars that no longer shine. So the life of a star after death is not a life of nothing. It is a life of presence, of memory, of transformation. It is the long cooling, the quiet motion, the subtle pull. And in this silence there is peace, the kind of peace that follows great effort, the kind that comes after long, hard work. A star does not resist this end. It has done its work. It has lit its sky, warmed its planets, burned for billions of years. Now it rests, not forgotten, but remembered in every orbit, every photon, every breath of gas that swirls through the dark. The next time you look at the night sky, think of the stars that no longer burn, the ones whose light we still see even though they have become something else. Their fire may be silent now, but it still lives, in us, around us, through us. Their glow still reaches across the distance, across time, not as a shout but as a whisper, not as a flame but as warmth. That is the gift of the silent fire. It burns even after burning ends. Let us move now into the deeper layers of this silence, where the fire has dimmed, yet the story continues. The white dwarf, this quiet, glowing ember of a former star, is not merely an end state. It is a laboratory in the sky, a relic that teaches us how matter behaves under pressure so intense that atoms lose their freedom. In its heart, the white dwarf is held up by quantum resistance, a kind of gentle rebellion where electrons refuse to be compressed beyond a certain point. This strange balance allows it to remain intact for billions of years, a monument to endurance, not explosion. These stars are often found scattered through the galaxy, drifting slowly along their stellar paths. They are too dim to be seen with the naked eye, and yet astronomers know them well. With the help of powerful telescopes, they can spot the subtle glows, measure their heat, chart their masses, and in doing so they uncover clues to the age of our galaxy. The oldest white dwarfs are like clocks, ticking not with motion but with cooling. The cooler the dwarf, the older the remnant. They serve as timekeepers for the Milky Way, silent historians of ancient cosmic fire. But not all white dwarfs are solitary. Some live in double star systems, where they share their space with another star. These stellar companions may be red dwarfs, aging giants, or even another white dwarf. In such systems, proximity becomes destiny. When two white dwarfs circle each other close enough, their orbits decay over time due to gravitational waves, a quiet leakage of energy through space-time itself. As they spiral inward, they draw closer and faster, until one of two things happens. They merge into a single larger white dwarf, or they reach the Chandrasekhar limit, triggering a runaway collapse. In those moments, the universe holds its breath. If the total mass exceeds the limit, about 1.4 times the mass of the Sun, the white dwarf cannot remain stable. Its internal pressure fails, and gravity, waiting patiently all along, rushes in. The star ignites in a thermonuclear flash, not gently like a nova, but catastrophically, as a Type Ia supernova. The explosion is so bright it outshines the entire galaxy for a time. These events are rare, but they are essential. They serve as cosmic measuring sticks, because their brightness is predictable. Astronomers use them to measure the distance to far-off galaxies and to understand how fast the universe is expanding. And in those explosions, heavier elements are cast into space. Iron, nickel, cobalt, metals that later become the cause of planets, the blood of living things, the strength of rocks and bones. Even in death, the white dwarf does not fade in vain. Its ending becomes a beginning elsewhere, scattered among interstellar dust, ready to seed the next generation of stars. Meanwhile, in the more stable systems where no explosion occurs, another kind of transformation begins. Over trillions of years, far beyond the current age of the universe, the white dwarf cools to the point that it stops emitting light altogether. Its atoms, once vibrant with thermal motion, settle into near stillness. This is the black dwarf, invisible, inert, cold, a body that has neither fusion nor glow. It is a fossil of a star, a final form reached not by force but by time's relentless patient unfolding. The idea of black dwarfs is theoretical, because the universe is still young. No white dwarf has yet cooled long enough to become one, but their existence is inevitable. In the far future, when the last stars burn out and galaxies grow dim, these black dwarfs will drift silently through space. They will not shine, they will not pulse, but they will still hold gravity. They will still carry mass. They will still curve space. Even then, they are not nothing. And what of the worlds left behind? Planets that once orbited the living star may still exist, moving around a white or black dwarf, like ghosts in an abandoned orbit. Some of these planets might retain atmospheres, others may be stripped to their rocky cores. Over time, their orbits may decay or shift. Some may fall into the star, disrupted by passing objects or slow gravitational loss. Others may be flung outward, becoming rogue planets, wandering the galaxy without a sun. But even these wayward worlds carry the fingerprints of their stars. Geological scars, mineral histories, chemical signatures written in stellar ink. In rare and curious cases, astronomers have even found evidence of debris disks around white dwarfs, thin rings of dust and shattered rock, likely the remnants of disrupted planetary bodies. These disks can slowly fall onto the white dwarf surface, and when they do, the elements leave telltale spectral lines in the light. In this way, we have discovered signs of old planetary systems, long dead, but still whispering through the atmosphere of a cooling star. In the spectrum of light, we read the final chapters of solar systems. Sometimes the white dwarf has no companion, no planets, no disks, only itself, alone in the dark. And yet, even in solitude, it holds beauty. Its crystal core, formed over billions of years as the star cools, slowly solidifies. The atoms arrange themselves into a lattice of carbon and oxygen, forming what could poetically be called a cosmic diamond. These crystalline hearts lie beneath the surface, hidden from sight, shining not with light but with structure. Perhaps, in some far future time, a civilization will find one of these cooled remnants and discover within it a record of a billion-year burn. This process, from white dwarf to black dwarf, from ember to fossil, is not destruction, it is aging, a long and peaceful sleep in the fabric of the galaxy. And we must learn to see this not as decay, but as legacy. Every white dwarf is a signature in time, a marker of a life lived in fire. It carried planets, it gave warmth, it moved comets, it anchored orbits, and now it watches. Slowly fading, yes, but always there. In our own sky, we see the white dwarf Sirius B, orbiting the bright star Sirius A. It is too faint to see without powerful tools, but it is there, tugging gently on its companion, circling in an endless loop. Its light is ancient, its mass immense, and yet it moves with silence and grace. It is not a failed star, it is a completed one. When the sun becomes a white dwarf, Earth may no longer be here. But the sun's core will remain, a dense, glowing memory of a star that once lit the days and fed the trees. It will not explode, it will not roar, it will simply cool, drifting slowly through time, perhaps with other dead stars in the galactic halo, a river of remnants circling the Milky Way. That too is a kind of beauty. To see the life of a star after death is to learn a new kind of reverence, not for brightness or power, but for persistence, for quietness, for what endures when the show is over. The white dwarf is not dramatic, it does not command the sky, but it stays. It waits, it cools, it remembers. And in this long silent burn, the universe reveals its slowest truths. Now let us follow this fire to its final breath, not with fear, but with gentle awe. The life of a star after death is not loud, nor is it lifeless. It is something in between, a quiet echo, a warm memory folded into the shape of matter. The star no longer burns, yet its influence endures. Its gravity still curves the paths of planets and dust. Its atoms still drift through space, joining new clouds, new beginnings. It is no longer a beacon, but it is not gone. It is the soft persistence of presence, the kind that asks for nothing and yet remains. In the far future, the universe will belong to these remnants. The brilliant main sequence stars like our sun will age and fade. The massive blue stars will live fast and die spectacularly, their lives measured in millions of years, but the small stars, the red dwarfs and their quiet cousins, will burn slowly for trillions of years. Eventually they too will extinguish, leaving behind white dwarfs that cool into black dwarfs. Over time the galaxy will grow dim, no new stars will form, the gas that once made them will be gone, used up, scattered, or locked in dead stars and cold planets, and what remains will be shaped by gravity and silence. Black dwarfs, if they exist by then, will dominate this dark era. They will be undetectable by light, but their mass will still bend space. They will be the fossils of a universe that once blazed. And as they drift, they may still meet, still interact. Occasionally two may collide, silently merging into a more massive body. Some might find their way into black holes, swallowed without a trace. Others will simply continue their path, orbiting invisibly through the galactic dark, circling nothing, pulled by no light. Yet even then, in this shadowed time, change will persist. On scales far beyond imagination, protons themselves may decay, slowly erasing the matter that makes up everything we know. If this happens, the black dwarfs will gradually evaporate into light particles, ghosting out of existence, not in an instant, but over quadrillions of years. Time stretched so far it no longer resembles time at all. A kind of final quiet, where even the silence fades. But this end is not without meaning. It is not a failure, not a disappearance. It is a cycle closing. The fire that once lived in stars is not gone. It became the planets, the oceans, the clouds, and even the eyes that once looked up to witness them. It became you, the atoms of your bones, your blood, your breath. They were once forged in stellar cores. You are not separate from the silent fire, you are the continuation of it. The cooling star lives on in your heartbeat, in the fire of your thoughts, in the gentle warmth of your skin under sunlight, which itself is a reminder that one star still burns, still glows. This connection is not just poetic, it is real. The calcium in your teeth, the phosphorus in your DNA, the iron in your blood, all were born in the bellies of stars that no longer shine. Every time you speak or move or dream, you are using matter shaped by the life and death of long-forgotten stars. You are a memory-given voice, a relic set in motion, a vessel of heat and light that has passed through time in silence before becoming sound again. Even the light from ancient white dwarves still reaches us. Some of the faint blue points in the night sky are these stellar remnants, still cooling, still glowing. Their light began its journey before humans built cities, before animals roamed, before Earth had air that could be breathed. When you look up, you are not just looking out, you are looking back, through time, through memory, through the life of fire slowed to a whisper, and in this whisper there is still learning. Astronomers continue to study white dwarfs to understand the age of star clusters, the cooling rates of stellar corpses, the composition of planetary debris. Every observation adds to the story. Every data point is a word in a sentence that spans galaxies. These dim stars, these silent fires are teachers. They show us how the universe ages, how it remembers, how it lets go. The future they point to is not one of despair, but one of transformation. The stars fade, yes, but what they give remains. Their dust forms the next layer. Their gravity guides the next turn. Their silence becomes the backdrop for new music. Even if light disappears, shape remains. Even if the sky goes dark, it still holds the fingerprints of what once was. And perhaps that is the deepest beauty, that the end is not empty, it is full of echoes. In this cosmic silence there is also hope. Not hope for light everlasting, but hope in the continuation of form, of matter, of influence. A star gives everything it has to the universe. It spends itself entirely, burning, radiating, creating elements. And then, when that fire runs out, it rests. Not as nothing, but as structure, as mass, as shape, as history. It does not ask to be remembered, but it is. In us, in planets, in dust, in the dark curves of space, and to sit beneath the stars and know this is to feel small but never meaningless. To know that you are not just watching the sky, but participating in it. That your very being is made possible by the lives and deaths of stars. That your shunt carries their glow, and that long after your own fire dims, the atoms of your body will carry on, cooling, drifting, maybe even seeding something new. You are a spark in a long chain of fire, each link connected by gravity, time, and the will to shine. So when the stars fade, do not fear the dark. It is not a loss, it is a continuation. A soft breath into stillness, a hand releasing the match after lighting the world. The silent fire is still burning even when it no longer glows, and in that silence the universe sleeps, waiting for what comes next. There is a moment, quiet and final, when a star forgets how to shine. Not suddenly, not with a scream, but with a kind of slow surrender. The fire inside fades, the fusion ceases, and gravity, waiting patiently for billions of years, finally gets its way. What happens next is not destruction. It is transformation, deep and total. The star folds in on itself, tighter and tighter, until even light cannot escape. What's left is not a thing in the ordinary sense. It is a place, a boundary, a silence so complete it becomes invisible. This is how a black hole is born, not from violence alone, but from forgetting. When light forgets to shine, space remembers to bend. To understand this process, we must begin inside a massive star. These are the giants of the cosmos, the ones that burn blue and white, fierce and fast. Their lives are brief by cosmic standards, only a few million years, but in that time they shine with incredible power. In their cores, hydrogen fuses into helium, then into carbon, oxygen, and heavier elements, layer upon layer, like the rings of an onion. The star burns hotter as it grows older, fusing heavier and heavier elements in a desperate race against collapse. But then it reaches iron, and here the race ends. Iron is the element that refuses. It cannot be fused into anything heavier without consuming energy. So when the core fills with iron, fusion stops. The outward pressure that held gravity at bay vanishes, and in a moment, the balance that defined the star's entire life is lost. Gravity surges inward. The core collapses, falling faster than the mind can comprehend. At the same time, the outer layers of the star crash inward too, rebounding off the dense core and exploding outward in a supernova, a final flash, a last cry. But at the centre, something new is forming. If the collapsing core is below a certain mass, it will stabilize as a neutron star, a city-sized sphere of neutrons, spinning and pulsing. But if the mass exceeds a critical limit, not even neutrons can hold back the collapse. There is no force in nature that can resist. And so the collapse continues, not just of matter, but of space itself. The star no longer has a surface, it no longer has a shape. It becomes a singularity, a point of infinite density and zero volume wrapped in an event horizon beyond which nothing, not even light, can escape. The birth of a black hole is the quietest kind of miracle. From the outside, nothing seems to happen all at once. If you were watching from a safe distance, the light from the collapsing star would stretch and dim, redshifted by gravity, frozen just above the event horizon. To your eyes, the star never quite disappears. It just fades, becoming slower, dimmer, softer, until it is gone, not by vanishing, but by being pulled beyond what light can tell. Time itself bends near a black hole. To the falling matter, the collapse takes moments. To a distant observer, it seems to take forever. This warping of time and space is not a trick of perspective. It is real. Einstein's theory of general relativity tells us that mass curves space-time, and the more mass is packed into a small area, the deeper the curve. A black hole is a curve so steep it becomes a well with no bottom. The edge of that well is the event horizon. Cross it and all paths lead inward. There is no escape, no turning back, no signal that can return. It is not a wall but a threshold, not a thing but a limit, where cause and effect no longer follow the rules we know. Inside the event horizon, all paths point to the singularity. The rules of physics as we understand them break down. The laws that govern atoms and energy, particles and forces, are stretched to their limits. We do not know what happens there. Our mathematics stops working. Some say time ends, others say it continues inward, in a direction we cannot imagine. It may be that new dimensions are born or that matter itself is erased. But in truth, we do not know. The singularity is the edge of understanding, a point not of nothingness but of mystery. And yet black holes are not invisible. We cannot see them directly, but we can see what they do. When gas and dust fall toward a black hole, they spiral in, forming an accretion disk that heats up and glows with intense energy. This disk can radiate in X-rays, lighting up the sky from millions of light years away. We see stars orbiting invisible points, moving so fast they must be circling something massive and unseen. We have even imaged the shadow of a black hole, light bent around the event horizon, captured by a network of telescopes stretching across Earth. What we saw was not the black hole itself, but its boundary, the edge of where light can no longer return. In this way, black holes are both destroyers and revealers. They consume matter, but they also illuminate the structure of space. They bend the paths of stars and shape galaxies. Most large galaxies, including our own, have supermassive black holes at their centers, millions or billions of times the mass of the Sun. How they formed is still uncertain. Perhaps from the collapse of many stars, perhaps from this early clumping of matter in the young universe. Whatever their origin, they act as anchors holding the motion of stars and dust in elegant spirals. And sometimes black holes merge. When two orbiting black holes draw close, they spiral inward, losing energy through gravitational waves. These waves ripple through space-time, stretching and squeezing the universe itself. In 2015, for the first time, humanity detected such a ripple, a whisper from two black holes merging over 1 billion light-years away. The signal lasted just a fraction of a second, but it told a story of unimaginable power. In that brief moment, more energy was released than in all the stars of the visible universe combined, and yet it passed through us quietly, like a wave through still water. This is the paradox of black holes. They are the loudest silence, the brightest shadow, the heaviest nothing. They mark the places where light once was and where it can never be again, but their presence is not absence. It is form beyond visibility. A black hole is a memory of a star compressed into a whisper so deep it cannot escape. It is light that forgot how to shine yet still shapes the night. To be near a black hole is to feel the pull of the ultimate goodbye, not just of light, but of time, of motion, of space itself. And yet, even in this farewell, the universe does not mourn. It simply continues, reshaped. Stars still form, galaxies still turn, matter still dances to gravity's rhythm. And somewhere quietly a star collapses, folds, becomes invisible, and begins a new story written in curves instead of light. Let us fall further now into the depths where light cannot follow. Beyond the event horizon lies a region that science cannot fully reach, a place not of emptiness, but of complexity so intense our understanding trembles. We know that time slows here, that space stretches, that all motion leans inward. But what truly happens inside a black hole is not known. It is the silence after a question never answered, the echo of a physics not yet written. And yet, through observation and theory, we can trace the edges of this unknowable centre, following the pathways of matter and energy as they spiral toward the unknown. Around a black hole, the space is not still. Matter falls in, but not immediately. It swirls, it heats, it lights up in a final flash before crossing the event horizon. This is the accretion disk, a brilliant ring of particles spiraling inward, colliding, heating to millions of degrees. In these disks, the material can glow brighter than entire galaxies. Jets of energy shoot from the poles, piercing space with columns of radiation. These jets are not made of matter from inside the black hole, but from particles near the edge, accelerated and ejected before falling in. Even in its hunger, the black hole cannot consume everything. The gravity near a black hole is so strong that it warps not only time, but also perception. Light bends around it in perfect arcs, creating what's called gravitational lensing. This bending allows us to see behind the object from the front, distorting the stars beyond it into rings or arcs. When scientists imaged the supermassive black hole in the galaxy M87, they did not see the black hole itself, but the silhouette it cast against the glowing backdrop of its accretion disk. The ring of fire encircled the shadow of absence, the closest we've ever come to seeing the invisible. Black holes come in many sizes. Stellar mass black holes are formed from individual stars, the remnants of supernovae. They can be 10, 20, maybe 50 times the mass of our Sun. Then there are intermediate black holes, harder to find but suspected to exist in star clusters and galactic bridges. At the largest scale are the supermassive black holes, found at the heart of nearly every galaxy. Ours in the centre of the Milky Way is called Sagittarius A. It is 4 million times the mass of the Sun, yet it fits within a space smaller than the orbit of Mercury. Its pull is slow but absolute. Stars near it move at astonishing speeds, tracing elliptical paths that tell us it is there, even if we cannot see it. The formation of supermassive black holes remains one of the great mysteries. Did they begin small and grow through mergers and feeding? Or did they form directly from immense clouds of gas in the early universe collapsing before stars even had time to ignite? The evidence is still uncertain, but one thing is clear. Their presence defines the structure of galaxies. Their gravity organizes stars, their energy shapes the gas from which new stars form, and their behavior is deeply entwined with the rhythms of cosmic evolution. And yet, despite their immense power, black holes are governed by surprisingly simple rules. Physicist John Archibald Wheeler once said, "Black holes have no hair." What he meant was that no matter what falls into them, gas or rock, light or time, the resulting black hole can be described by only 3 properties: its mass, its spin, and its charge. The complexity of the matter that fell in is erased. All that remains is a smooth, featureless object defined by these 3 values. The information, the identity of what once was, appears lost. This loss of information is one of the most puzzling questions in physics. According to quantum theory, information about a system is never truly destroyed. But if matter disappears into a black hole and is never seen again, what happens to that information? Does it vanish? Is it stored somehow in the surface of the event horizon? Could it be released through Hawking radiation, the slow evaporation of the black hole over trillions of years? These questions strike at the core of how we understand reality, and we do not yet have the answers. Hawking radiation itself is a remarkable idea. Proposed by Stephen Hawking in 1974, it suggests that black holes are not entirely black. Quantum fluctuations at the edge of the event horizon can cause pairs of particles to form. One falls in, the other escapes. The escaping particle takes a bit of the black hole's energy with it. Over immense timescales, this radiation would cause the black hole to shrink, fade, and eventually vanish. If true, then even these titans are not forever. Even darkness ends, but this ending is so far in the future that it defies imagination. A black hole with the mass of the Sun would take 1067 years to evaporate, a time so long it makes the age of the universe, a mere 14 billion years, seem like a blink. Larger black holes would last even longer. In that distant era, when the stars have died and galaxies have dispersed, black holes will remain. The final authors of gravitational curvature, the last keepers of cosmic weight. Their radiation, faint and slow, will be the only light in a universe grown dark. And so they will fade, not with a bang, but with a whisper. The last remnants of stars collapsing into pure gravity, now undoing themselves, one particle at a time. Even in their fading, they are teachers. They show us how energy persists, how space responds to pressure, how mass folds into geometry. They are the laboratories of extremes, the crucibles where the universe tests its limits. It is strange to think that something so mysterious, so silent, so hidden, can have such reach. Black holes influence not just the space around them, but our understanding of physics, of time, of causality itself. They ask questions we cannot yet answer. What happens at the singularity? Can information ever escape? Is there a boundary to understanding? Or is the universe always one step deeper than we can see? Perhaps black holes are not barriers, but bridges. Some theories suggest that inside them lies a wormhole, a tunnel through space-time to another point, another place, another universe. These ideas are not proven, but they remind us that our limits are not the universe's limits. Where we see darkness, there may be passage. Where we see collapse, there may be connection. In every black hole is the shadow of a star that once gave light. Its light is gone, but not its mass, not its pull, not its place in the story. When light forgets to shine, gravity does not forget to hold. The star's voice may be silent, but its influence is still spoken in orbits, in spirals, in warps. A black hole is the echo of illumination curved into permanence, so let us not fear the dark. Let us respect it, for it holds not just what we cannot see, but what we are not yet ready to know. Now let us rest for a moment at the edge, the event horizon, that invisible veil where the known ends and mystery begins. A black hole is not just an object, not just a collapsed star. It is a message written in the curvature of space-time, a reminder that even the brightest fire must one day give way to gravity's embrace. What began as fusion and flame has now become silence and pull, but in that silence is meaning. A black hole is what remains when light forgets to shine, and yet in forgetting, it leaves behind a map, a way to trace the shape of what was, and perhaps of what may still become. It's tempting to think of a black hole as the end of a story, but in the universe there are no ends, only changes. The star did not disappear. It transformed. Its mass still exists. Its gravity still shapes. Its influence still ripples outward, bending light and time alike. Even in invisibility, it is not erased. A black hole is a lesson in presence without appearance. It cannot be seen, but it can be known. It cannot be touched, but it can be felt through the sway of nearby stars and the rhythm of space itself. Imagine a world orbiting just outside the event horizon. It would be bathed in distortion. The light from the sky would bend into rings and arcs. Time would pass differently, and the black hole would dominate the view, not as a whole, but as a shadow surrounded by brilliance. The closer you move toward it, the more the world stretches, both around you and within you. Seconds slow, shapes lengthen. Sound cannot reach you. Everything curves inward, and if you crossed that final threshold, you would fall, not quickly, but eternally. To the outside world, you would appear frozen in time, forever approaching, but never quite arriving. But you would feel the fall, not as motion, but as surrender. The laws you lived by would dissolve. Inside the event horizon, there is no stopping, no turning. All directions lead inward, not because of some cosmic punishment, but because that is how gravity shapes the fabric of space at its deepest. A black hole is the final conclusion to mass under pressure, a singularity hidden behind the curtain of physics. And while we do not yet know what lies within, we know that something still resides there, something dense, silent, waiting. Yet even here, at this edge of knowledge, the universe gives us more than darkness. It gives us clues. It gives us gravitational waves, ripples in space itself that reach across billions of light years to whisper of collisions, of unions, of black holes merging and reshaping. These waves pass through Earth unnoticed by our bodies but captured by our instruments. When we detect them, we are listening to the heartbeat of the invisible. We are eavesdropping on the language of gravity, spoken not in light but in motion. And this language is changing how we understand everything. With each signal, we learn more about the population of black holes in the universe, how many there are, how massive they can be, how they move and meet. We begin to chart the dark not just by absence but by influence. We begin to map not what we see but what we feel. And that is the gift of black holes. They show us the universe beyond vision. As we look further ahead into the farthest futures of time, black holes take on a new role. In a universe where all stars have died, where galaxies have stopped forming, and where even atoms begin to decay, the black holes will remain. For countless ages, they will drift in the quiet dark, swallowing what little mass remains. They will be the last sculptors of structure, the final architects of gravity, until even they begin to fade. Through the slow process of Hawking radiation, each black hole will eventually release its energy back into the cosmos. Not quickly, not loudly, but patiently. A sun-sized black hole might take 1067 years to fully evaporate. A supermassive one might persist far longer. And yet one by one they will fade, not into nothing, but into the cold bath of low-energy particles. The universe will not end in fire, but in fading. A slow unweaving of mass into light, light into silence. And then, perhaps, something new begins. Some physicists wonder whether the end of a black hole might be a beginning elsewhere, that as matter collapses inward beyond the horizon, it might be funneled into a new region of space, a baby universe, blooming from the singularity like a seed breaking through soil. This is speculation, of course, but it reminds us that the end of understanding is not the end of wonder. Black holes are not just astronomical objects. They are philosophical doors. They ask us to imagine what comes next. Because even as light forgets how to shine, memory persists. The memory of mass, of movement, of transformation. The black hole remembers the star it once was, even if that memory is hidden. And we, observers in the vastness, carry that memory forward. Every time we measure a bent light, or track a spiraling star, or detect the faint whisper of a wave in space, we are retelling the story of collapse, the story of silence, the story of what happens when the brightest becomes the deepest. There is something beautiful in that reversal. The brightest stars become the darkest objects, the most visible become the most hidden. But the truth is never lost. It is stored in form, in mass, in pull, in the invisible lines that shape the visible world. The stars die, but their gravity remains. Their influence continues. Their absence sculpts what stays. And so we return gently to our own place beneath the stars. We look up at the night sky and see points of light, some young, some old, some already gone. Among them, unseen, are black holes, the remains of stars that once burned, now folded into silence. We cannot see them, but they are there, holding stars in orbit, creating jets of energy, whispering across space. Their darkness is not despair, it is depth, it is distance, it is the place where light rests. In this cosmic stillness, we find not an ending, but an invitation, to think more deeply, to wonder more freely, to respect the places we cannot yet go. Black holes are not empty. They are full of unanswered questions. They are the places where the universe keeps its secrets just beyond reach, always calling us forward. So let the light forget to shine. Let it fall inward. Let it curve. Let it vanish from sight. In doing so, it teaches us how to feel the shape of the universe without needing to see it. It teaches us that even when the flame goes out, the story continues. And in that continuation, there is something vast and quiet and sacred. Something we might never touch, but always feel. Long before you were born, long before earth cooled, or oceans rose, or trees whispered their first breath, a star died. It did not vanish quietly, it burst. In one final act of brilliance, it scattered its bones across the sky. Those bones became dust, and that dust became the seeds of everything. It drifted, cooled, clung to gas, gathered into clouds. It shaped new stars, new worlds. Some of it fell into earth, into rain, into rivers, into roots. Some of it found its way into you. This is the story of how dying stars do not disappear. They become the beginning again. The stardust echoes. And through those echoes, the universe remembers how to begin. When a massive star nears the end of its life, it swells into a red supergiant. It is vast and unstable. its core burning through the periodic table, fusing heavier and heavier elements with frantic urgency. Hydrogen becomes helium, helium becomes carbon, then oxygen, silicon, and iron. But when iron appears, the clock runs out. Fusing iron takes more energy than it gives. The star begins to fold, the core collapses under its own weight, and the outer layers rebound violently in a supernova, a brilliant, catastrophic bloom. In that explosion, temperatures surge to levels not seen since the birth of the universe. Elements heavier than iron are forged in moments. Gold, platinum, uranium, and others, blasted into space by shockwaves that rip through the dying star's body. This process, called nucleosynthesis, is the alchemy of the cosmos. It is where the raw materials for planets, plants, and people are born. Each atom of calcium in your teeth, each bit of iron in your blood, was once part of a star's last breath. After the supernova fades, what remains is a cloud, a nebula, expanding outward in tendrils and waves. These remnants glow with the light of radioactive decay and lingering heat. They drift for centuries, spreading into the interstellar medium, mixing with hydrogen and helium that have never been part of a star. And slowly gravity begins its patient work. These clouds gather again, pulled into denser knots, stirred by nearby stars and galactic winds. Where the dust thickens enough, new stars are born, and around them new planets, each one made in part from the ashes of the old. This is the great recycling of the universe. Matter is never wasted. The atoms in your body are second-hand, and in some cases, third or fourth-hand, borrowed from suns long dead. And yet they remain whole, functional, beautiful. The carbon that carries your cells once danced inside a star. The nitrogen in your DNA was forged in stellar fire. You're not just made of stardust. You're made of its echoes, the repetition of creation through destruction, of endings folded into beginnings. Not all stars end in supernovae. Smaller stars, like our Sun, die more gently. They expand into red giants, shedding their outer layers in waves of gas and dust. These shells of material drift away slowly, lit from within by the remaining hot core, a white dwarf cooling in silence. The surrounding gas forms a planetary nebula, glowing with soft colours and gentle symmetry. Though not as violent as a supernova, this death still releases vital elements into space: carbon, nitrogen, oxygen, all of which play roles in life as we know it. The dust from these stellar deaths is incredibly fine, smaller than smoke yet rich in complexity. It contains tiny crystals, molecules, and sometimes even complex organic compounds. These particles travel for eons, crossing the gulfs between stars. They are carried by stellar winds, by magnetic fields, by the turning wheels of spiral galaxies. They collect in molecular clouds, in icy comets, in asteroids and meteorites. Some of them fall to planets, some of them fall to Earth. Here they become part of soil and sea, of bone and breath. When we dig deep into the ground, we find stardust trapped in ancient rock. When we look at meteorites, we see grains older than the sun, untouched by time except for the journey. And when we look into ourselves, we find the same materials arranged into the machinery of life. The carbon in your skin, the oxygen in your breath, the phosphorus in your thoughts, all of it began in stars. All of it arrived here, not with intention, but with gravity and chance. This process of seeding the universe is not random. It follows patterns. Stars are born in nurseries, regions dense with gas and dust, like the Orion Nebula or the Eagle Nebula. These clouds, sculpted by starlight and winds, give rise to clusters of stars, often with planets in tow. Some will live long, others will die quickly, repeating the cycle. As each generation of stars burns and dies, the galaxy grows richer in heavy elements. This is called galactic chemical evolution. It's why older stars contain mostly hydrogen and helium, while younger ones, like our Sun, are metal-rich. The universe matures by remembering its deaths. And so, when you stand beneath the stars and see their cold, twinkling light, you are looking at a vast network of memory. Some of that light comes from stars still burning, some from stars already gone, some from clouds preparing new stars in their silent, swirling folds. But all of it, every photon, is part of a long lineage: light from creation, light from collapse, light from dust that once burned, cooled, and came together again. Even in distant galaxies, we see the same process. Spiral arms littered with bright young stars, nebulae glowing with the heat of birth and the ash of death, supernova remnants marking the graves of once mighty suns. These echoes are not faint. They are the heartbeat of the cosmos. Without them, there would be no gold in our rings, no oxygen in our air, no planets to stand on. Without them, there would be no us. And this is the paradox. Stars must die for life to exist. It is in their dying that the ingredients for life are made. The universe does not create life directly. It creates stars. And the stars, in burning and breaking, scatter the materials that life needs. It is a slow, patient process. But it works. Over billions of years it has worked again and again. You are proof. To be made of stardust is not just a poetic idea. It is a physical truth. You are composed of atoms forged in fire and scattered in wind, collected in rock and rain, arranged into cells and thoughts. The stars made you piece by piece over time beyond time, and now you look back at them trying to understand how such violence gave rise to such stillness, how such distance gave rise to such closeness. The answer lies in the dust. The dust remembers, the dust tells, and the dust is not gone. It is here. Let us follow the stardust now, not just as particles drifting through space, but as quiet travellers carrying memory. Each grain, though impossibly small, contains within it the entire history of transformation. It may look like soot, like smoke, like nothing more than a speck, but it is a fragment of fire, cooled and reshaped. These grains begin their journey in stellar winds, in explosive shells of dying stars, and they end up in places beyond imagination, folded into the hearts of comets, hidden in the crusts of planets, or breathed in and out by living lungs. The story of stardust is not about what ends, but about what continues, subtly and beautifully, forever. The journey from star to stardust begins in heat, furnaces where atoms fuse and are scattered. When stars die, they cast off not only gas, but solids. Carbon condenses into graphite or diamond-like structures. Silicon combines with oxygen to form tiny silicate crystals. In the outer layers of red giants, complex molecules form long before the final breath. When these stars shed their atmospheres, these particles are set free, travelling outward at speeds measured in kilometres per second, expanding into the interstellar medium like ripples in a pond. They mix with other materials, are stirred by passing shock waves, are nudged by magnetic fields. And slowly they gather. In vast clouds, cold, dark, quiet, these grains settle. Molecular clouds, they're called, and they are the coldest places in the galaxy, just a few degrees above absolute zero. Here, where light barely penetrates, dust begins to collect more dust. Gravity tugs gently. Tiny clumps form. Over millions of years, these clumps grow, drawing in gas and more dust, until a core forms hot enough for fusion. A new star is born, and around it a disk of leftover material swirls, flattened by rotation. From that disk, planets emerge, moons, asteroids, the architecture of a new solar system built from recycled light. In this way, every planet you've ever heard of is a product of dust. Earth itself formed from a disk rich in heavy elements, iron, nickel, silicon, carbon, all inherited from stars that died long before the sun was born. The core of our planet is metal, drawn downward by gravity, left behind by massive stars that exploded in ancient skies. The crust is layered with minerals that formed in fire, cooled, compressed. And within the thin envelope of atmosphere and water, life emerged, built from carbon, energized by sunlight, held together by atoms that have passed through stars. And it is not just Earth. The entire solar system is laced with stardust. Meteorites that fall through the sky often contain pre-solar grains, microscopic crystals that predate the sun itself. When scientists examine them under microscopes, they find isotopic signatures that do not match anything formed in our system. These grains are older than Earth, older than our star, formed in supernovae and red giants that existed before the solar system began. They are time travelers, preserved in stone. But stardust does not stop at structure. It reaches into biology. The same elements forged in stars are the ones that make life possible. Carbon, the backbone of organic molecules. Oxygen, crucial for respiration and water. Nitrogen, found in DNA and proteins. Phosphorus, present in energy storage and genetic code. Sulfur, in enzymes and amino acids. All of these elements originated in stellar cores and were scattered in deaths that seemed, from a distance, to be destruction. But they were instead offerings, material gifts sent across time and space waiting to be assembled. This is the essence of life, not separate from the stars, but emerging from them. When you eat, you're consuming elements forged in stars. When you breathe, you're drawing in molecules that began in supernovae. When you think, your thoughts arise from the firing of neurons built from carbon, oxygen, hydrogen, all once part of cosmic fire. You're not merely in the universe, you are of it. You are the voice of stardust, wondering where it came from, and you are not alone. Everything that lives shares this origin. Trees pull carbon dioxide from the air and use it to build leaves, bark, and fruit. The carbon they use once belonged to ancient stars. Fish swim through water made from oxygen and hydrogen, one from stellar fusion, the other from the birth of the universe itself. Even bacteria, the oldest life forms on Earth, are shaped by elements that existed long before life began. Life is what matter does when given the right conditions and enough time, and matter is what stars leave behind when they die. In this way, death fuels life. The stars do not end when they explode. They become seeds, and those seeds grow in silence. They form worlds and winds and weather. They shape mountains and rivers. They are inhaled by creatures who do not know they are breathing stars, and yet the process is real. It continues every moment. Right now, in distant galaxies, stars are dying. Right now, dust is drifting through the void. Right now, new stars are forming, their light still travelling toward us, and in 1,000 years or 10,000, some of that dust may reach a planet. It may settle on a leaf, or it may rest in the bones of something that has not yet been born. And this story of stars dying and seeding the universe is not rare, it is the norm. The galaxy is filled with death and rebirth. It is not a place of stillness, but of motion, of cycles, of change. Stars live, die, and give. Planets form, evolve, and inherit. Life arises, reflects, and remembers. And in this loop, meaning is made, not because the universe intends it, but because it allows it, because it does not erase what was, it builds upon it. Even now, when you walk through a forest or hold a stone or drink from a glass of water, you are touching the results of this great stellar generosity. You are participating in it, you are continuing it, and you are not alone. Every person you have ever loved, every book ever written, every idea ever imagined, all of it happened in matter that came from stars. Stardust is not just the building block of life, it is the common ground of being. It is humbling to think that the stars had to die for us to live, but it is also beautiful, because it means that we are the result of cosmic generosity, of explosions that gave more than they took, of endings that turned themselves into beginnings. The stardust did not ask to be noticed. It did not demand purpose, but it simply followed the rules of nature, moving, bonding, drifting, changing, until one day it opened its eyes and asked, "Where did I come from?" And here is the answer. You came from stars. You came from silence and light and fire and time. You came from the echoes of deaths that lit the sky. And now you shine in your own way, quietly in thought and word and love. You are a new echo, a soft continuation, a dust that remembers. Now let us bring the dust home. It floats not only in deep space or the far reaches of nebulae, but here, on windowsills, on the wind, in the quiet corners of your breath. The very air you inhale contains molecules born from stars, scattered through the solar system and gathered here by gravity and chance. You are not beneath the stardust, you are inside it. The same particles that once drifted through glowing clouds now rest in the cells of your skin, in the blood moving quietly through your heart. The cosmos is not something out there, it is folded within you. And so we begin to see the true nature of a star's farewell. It is not a departure, it is a distribution. The atoms do not vanish when a star explodes, they are gifted, cast out into the great dark, where time is long and movement slow. These atoms drift through interstellar space, cooling, waiting. They mix and intermingle sometimes for millions of years before finding their way into the new clouds of gas. And in those clouds, the universe begins again, not as a duplicate, but as a continuation. New stars form from the ashes of the old, and around them, new planets gather. Each one is stitched with the memory of previous light. Our sun is one such star, a second-generation light, born from the remains of older stars that died billions of years ago. That is why the sun, unlike the first stars, contains heavy elements. It inherited them, and because it did, the planets that formed around it could also contain those materials. Earth is a rocky planet, not just because of position or size, but because of the stardust it was made from. Its metals, its minerals, its carbon and oxygen, all were forged long before the Earth was born. Our planet is not a singular creation. It is an accumulation of many cosmic histories layered into one. And what Earth became is extraordinary. Life arose not instantly, but patiently, slowly. Over billions of years, the elements learned to arrange themselves into cells, and then into patterns, and then into minds. Every time you think, or dream, or cry, your body is using chemistry that began in stars. Your emotions are not separate from physics. They are made possible by it. The sadness you feel in parting, the joy of reunion, the awe of looking up at the stars. These are stardust expressing itself in the language of life. Some of the stardust that formed Earth still wanders. It was never caught in a planet or a moon. It lingers in comets, in icy fragments on the outer edge of the solar system. It orbits in the asteroid belt. It drifts in clouds of interplanetary dust. And sometimes it falls to Earth. Meteor showers are cosmic returns, tiny pieces of comet dust burning up in our atmosphere, glowing briefly as they give their last light. When you see a shooting star, you are witnessing a grain of ancient material finishing its journey in a blaze, a final echo of a journey that began in the death of a star. There is poetry in the fact that the death of stars leads to both beauty and necessity. Without dying stars, there would be no iron for blood, no carbon for cells, no gold for rings, no silicon for circuits. Every tool you hold, every home you build, every breath you take, it all begins in the fire of a distant extinct sun. And still, more are being made. In distant galaxies, stars are dying even now, scattering the seeds of future planets, future beings, future questions. And yet, stardust does not only build the material world, it builds the inner one too. Knowing where you come from changes how you see. It softens the boundary between the personal and the cosmic when you realize that your hands were once inside stars, that your bones are echoes of ancient explosions, that your eyes are made from the same materials as the stars you gaze upon. It becomes difficult to feel alone. The separation between self and sky dissolves. The universe is not outside of you, it is in you, and you are in it. Perhaps this is why stargazing feels sacred. It is not just light we are looking at, but history, not just distance, but return. The starlight that reaches you tonight began its journey long ago, when dinosaurs still walked the earth, or when the earth was still molten, or before Earth existed at all. You are seeing photons that have crossed time and space to reach your eyes, unchanged, unbroken. That starlight was cast into the dark, and it found you. In that moment, you become part of something immense, not because you are large, but because you are connected. The same laws that govern the fall of comets and the fusion in stars also guide the chemistry in your body. The same elements that drift through nebulae run through your veins. The same dust that formed planets rests in your fingernails. You are a structure held together by gravity and time, alive in a universe that allows such complexity to bloom. And when your life ends, those elements will return to the earth, to the air, to the cycle. You will not disappear. You will change form. The carbon in your body may one day be part of a tree or a breath or a river. Your atoms will scatter and find new shapes, new stories. In a very real way, you will seed the future, just as the stars seeded you. This is the great continuity, not just of matter, but of motion, not just of form, but of purpose. The universe does not waste, it transforms, it folds what was into what will be, and through that process, stardust echoes, not just through stars and planets, but through people and poems, through dreams and songs, through the endless asking of where we came from and what we are. So let the stardust settle into you. Let it remind you that your existence is not a random flicker, but a flame carried across generations of fire. You're not small in meaning, you're vast in connection, and somewhere beyond the sky you see, a star is dying right now. Its light will one day reach a world not yet formed. Its dust will one day build hands not yet imagined. And those hands may one day raise themselves to the stars and whisper, "I remember." In the stillness after a star's death, something strange remains. It does not shine like it once did. It does not roar or explode, but it spins, it pulses. It holds mass with such fierce density that space itself leans inward. This is a neutron star, a ghost of a sun, born not from fire, but from collapse. It is what's left when gravity wins and light gives way, and though it no longer burns, it remembers. It remembers the mass it once held, the atoms it once shaped. A neutron star is the compact memory of a life once brilliant, and in its silence it speaks the language of gravity, time, and endurance. To understand a neutron star, we must begin at its origin. It comes from a star much larger than our own. These massive stars live fast and hot, fusing elements in their cores until iron appears. Iron does not yield energy through fusion, so when a core fills with it, the balancing act that held the star together fails. Gravity takes over. The core collapses with unimaginable speed. Electrons and protons are crushed together into neutrons, and in a fraction of a second, the star's heart becomes something entirely new, a neutron-rich sphere so dense it defies comprehension. The outer layers of the star rebound against this new core, and the result is a supernova, a brilliant flamboche that can outshine entire galaxies. But the real miracle lies in what's left behind. A neutron star is barely 20 kilometers wide, yet it holds more mass than the Sun. A sugar cube-sized piece of neutron star would weigh as much as a mountain. It is matter crushed into nearly pure nuclear density. It has no surface in the way we understand. It is a solid wave of neutrons, smooth and strange, held together not by chemistry or structure, but by the raw laws of quantum physics. And yet it spins rapidly. Some neutron stars rotate hundreds of times per second. This spin is a relic of the star's collapse. As it shrinks, it spins faster, like a skater pulling in their arms. These spinning neutron stars, called pulsars, emit beams of radiation from their magnetic poles. If these beams sweep past Earth, we detect them as rhythmic pulses, perfect, steady, precise. Some pulsars are so regular their timing rivals atomic clocks. We use them to track time, to map gravity, even to detect gravitational waves. The ghost of a star becomes a tool, a beacon, a signal that cuts through cosmic silence. Neutron stars are magnetic monsters. Their fields are trillions of times stronger than Earth's. These magnetic fields twist and coil, trapping particles, creating storms of radiation that crackle across their surfaces. In the most extreme cases, we find magnetars, neutron stars with magnetic fields so intense they can alter atomic structures. A magnetar flare could wipe clean the electronics of nearby planets, rearrange molecules, unleash more energy in a tenth of a second than the Sun releases in a year. Yet even magnetars cool. They age, they fade into quieter forms, still spinning, still dense, but no longer volatile. The surface of a neutron star is smooth, hard, and alien. There is no crust in the way we imagine. The outer few centimeters may be iron nuclei packed into a crystalline lattice, but below that is a sea of neutrons, held together by nuclear forces. There are no mountains, no rivers, just gravity so strong that even light bends to follow its curve. If you dropped a pebble from a meter above, it would hit the surface in a microsecond, striking with the force of a bomb. There is no softness here, only precision, pressure, and memory. These stars do not live alone. Some orbit companions, other stars, or even other neutron stars. In binary systems, they can draw in matter from their neighbours, forming glowing disks of hot gas. This accretion can increase their mass, spin them faster, or even ignite brief flares of X-rays. When two neutron stars orbit each other closely, they lose energy through gravitational waves, spiralling inward until they collide. This merger, called a kilonova, releases gold and platinum, sends out gravitational waves and can leave behind a black hole, or a new heavier neutron star. We detected such a merger in 2017. Telescopes across the world watched as light and gravity arrived together, telling the same story in different languages. The collision gave us gold, but also confirmation. Neutron stars are not just theoretical. They are real, dynamic, and essential to the fabric of the cosmos. Without them, we would not fully understand gravity. Without them, we might not exist, because the elements they create are part of what we are. And still, most neutron stars are quiet. They spin unseen, deep in the arms of galaxies. They drift, cold and steady, holding their mass, their magnetism, their memory. They are the fossils of supernovae, the husks of stars too massive to live gently, too small to become black holes. And in their silence, they offer a kind of truth, that not all light is visible, not all heat is felt, and not all life must glow to be important. Some stories are dense, some are small, some are wrapped in gravity, waiting to be noticed. Neutron stars are also laboratories, places where physics can be tested under extreme conditions. In their depths, we might find exotic forms of matter, hyperons, quark-gluon plasmas, even states we do not yet have names for. We cannot replicate their pressure on Earth. We cannot mimic their density, but we can listen to their signals, study their spins, map their pulses, and imagine what lies within. They are clues to deeper laws, hints of a universe more complex than our equations can fully grasp. And there is something poetic in that. The death of a star instead of erasing meaning deepens it. What once radiated freely now compresses into precision. What once filled space with light now folds into density, into timekeeping, into the shaping of other stars. These are not ruins, they are monuments. They do not speak loudly, they do not demand our attention, but they endure. They hold gravity in place, they remember. To stand beneath the stars and know that some of them have already collapsed, already transformed, already become these spinning ghosts, and yet their echoes still reach you, is to feel time in your bones. The light you see is not always the present. The darkness you feel is not always absence. Sometimes it is density, sometimes it is waiting, sometimes it is the memory of mass, coiled so tightly it has become invisible. Let us drift now beyond the flash of their birth, into the long, quiet lives of neutron stars, their steady spins, their ghostly lights, their memory of mass suspended in silence. These stars are not gone, they are waiting, watching, speaking not with light, but with rhythm. When you hear the pulse of a neutron star, you are not hearing sound, but time condensed into rotation, into radiation, into a whisper that travels across galaxies and arrives intact in the antennas of Earth. It is the ticking of something ancient, something that survived death and chose to continue. Some neutron stars spin at terrifying speeds. These are the millisecond pulsars, remnants that rotate hundreds of times per second. Their light sweeps across space in beams, and when that beam hits our detectors, it appears as a regular pulse. These pulses are so precise they rival the most accurate clocks humans have ever built. Scientists use them to study gravity, to search for planets, and even to attempt something extraordinary, a galactic navigation system where future spacecraft might one day use pulsar signals like cosmic GPS. And still, some of these stars do more than spin. In rare cases, they glitch. For a brief moment, their spin rate suddenly changes. This is not a failure, but a message from within. A neutron star's crust, though solid and incredibly strong, can sometimes crack under the pressure of its rotation and magnetic fields. These starquakes release bursts of energy and cause the entire star to adjust its spin. Imagine something denser than the sun shuddering just a little, and the whole universe noticing. This is not just astrophysics, it's the sound of cosmic memory shifting in its sleep. Inside the crust, deeper still, strange things may be happening. The matter in a neutron star is not like anything on Earth. Beneath the iron-like shell lies a sea of superfluid neutrons, a state of matter that flows without friction. This ocean may rotate differently than the outer crust, and when the two interact, glitches occur. In this quiet, collapsed world, fluid and solid coexist in a dance no eye can see. It is quantum mechanics on a stellar scale, spinning and stretching in a form that may never be touched, but always felt. Some neutron stars are born with companions. In binary systems, they orbit close to another star, and as that partner evolves, swelling into a red giant or collapsing into a white dwarf, It may spill material onto the neutron star. This flow of gas creates an accretion disk, glowing hot as it spirals inward. The neutron star feeds on this material, gaining mass, spinning faster. Sometimes it awakens from apparent silence and begins to pulse again, revived by the touch of its companion's outer layers. These are recycled pulsars, ghosts that were quiet and now speak again. And when two neutron stars orbit each other, the story becomes even stranger. As they spiral inward, their orbit shrinks, their speed increases, and the energy they lose radiates as gravitational waves. These waves are not light or sound, they are ripples in the very fabric of space-time, stretching and squeezing the universe itself. When they reach Earth, they pass through everything, through mountains, oceans, even through us, without leaving a trace we can feel, but our instruments feel them. And in their detection, we confirm what Einstein imagined a century ago, that space is not empty and time is not flat. The collision of two neutron stars is one of the most powerful events in the universe. In the final moments, as they approach one another, their surfaces may stretch and deform, bulging under tidal forces. Their magnetic fields twist together, and then in an instant they merge. The energy released is extraordinary. Gold and platinum are forged in that moment, along with a flash of light and a deep gravitational breath. Sometimes what remains is a heavier neutron star. Sometimes the core collapses further and becomes a black hole. Either way, what was once two stars has become one, changed, condensed, continued. From Earth we watch, telescopes point toward the flash, radio antennas listen for the pulses, gravitational wave detectors wait for the subtle tug, and when all three signals arrive, light, waves and particles, we see the universe in stereo. We witness a single event from multiple angles, and suddenly the invisible becomes known. This is the era of multi-messenger astronomy. Neutron stars are not just curiosities, they are keys, revealing the behavior of matter under pressure, the reality of gravity under stress, and the unity of forces we once thought separate. But perhaps the strangest neutron stars of all are the magnetars. These rare objects possess magnetic fields so strong they can twist atoms out of shape. A single magnetar placed halfway to the moon would erase the data on every credit card on Earth. Their surfaces can crack under magnetic pressure, unleashing giant flares, bursts of gamma rays that cross the galaxy in seconds. Some scientists believe certain mysterious fast radio bursts, millisecond-long flashes of radio energy from distant galaxies, may come from magnetars flaring in the dark. They are stars that died and then learned to scream. And yet for all their power, neutron stars age. They slow down. Their magnetic fields decay. Their pulses fade. Over millions or billions of years they become quiet again. No longer beacons, just dense, cold remnants. Dark stars moving through space, leaving no light behind. Some may still carry planets, remnants from when they were young. A few such planets have been found. Dark worlds orbiting collapsed suns, circling ghosts, warmed not by light, but by the memory of what once was. To imagine standing on one of those worlds is to imagine a night sky, forever dark, yet curved by immense gravity. Time would move differently. Space would feel bent. The parent star would be a sphere of silence, massive but almost invisible, pulling everything close. And in that closeness, a kind of intimacy. A reminder that life, if it can exist in such places, would be shaped not by heat, but by pressure. Not by light, but by endurance. Neutron stars remind us that not all energy is obvious, that not all life is born in brightness, that the heaviest things can also be the most precise. Their very existence tells us that matter is flexible, that it can adapt to conditions beyond imagination. They stretch the boundaries of what is possible, crushing atoms, bending space, ticking with unimaginable speed, flaring with invisible light. And they do it all from a place of apparent stillness. These are not the roaring giants of the early universe. They are the compact survivors, the quiet witnesses, the concentrated proof that stars remember how to hold on even after their fire is gone. They are the weight of history, condensed into rotation and rhythm. They are what gravity makes when it is allowed to speak fully. And what it says is this: even after collapse there is form, even after silence there is signal, even after death there is memory. So when you next look up into the stars, know that some of the brightest have already folded into themselves. Know that some of the light you see was sent by stars that are now small and dark, yet still moving, still shaping, still marking time in invisible beats. And know that among them are the ghosts of suns, dense, spinning quiet, and that they are not lost, they are only listening. Let us remain with these remnants a little longer, in the still gravity of their presence. Neutron stars do not ask to be seen. They do not shine with the warmth of sunlight or burn with the brilliance of a nova. Instead, they persist, dense, silent, exact. Their lives are not measured in flames but in rotations, in pulses, in gravitational echoes that stretch across space. In a cosmos so often defined by light, they remind us that darkness too can hold beauty, that what does not illuminate may still inspire. That what has collapsed is not lost, only changed into another way of being. As time stretches forward, neutron stars slow. Their rotations, once furious, begin to decelerate. Their pulses soften. The energy they emit, once focused and fierce, begins to fade. They become radio quiet, no longer sending out the beams that mark their presence across the galaxy. But even in that silence, they continue. They drift through the Milky Way, orbiting its center, passing through arms of gas and dust. They become invisible travelers, moving through a galactic ocean made, in part, from the remnants of stars just like them. They are everywhere and almost nowhere, felt, not seen. Occasionally, a neutron star will pass near another object, another star, a planet, a gas cloud. Its gravity may alter orbits. Its magnetism may stir particles. It might capture debris or, in rare instances, collide with something else. These moments of interaction are brief, dramatic, and rare. But most neutron stars live alone, not because they chose to, but because their origins were violent enough to scatter everything around them. Many neutron stars were given a kick at birth, flung outwards by the asymmetry of the supernova that formed them. Some move at hundreds of kilometers per second, racing through space like silent bullets. And yet, in that motion they carry stories. Their speed is memory. Their direction is history written in trajectory. The question often arises, can something so extreme, so dense and strange, ever give rise to life around it? While improbable, it is not impossible. Theoretically, if a neutron star had a planet in a stable orbit, and if that planet retained enough heat or received energy from the star's magnetic field or accretion disk, it might host exotic forms of life. Not life as we know it, sunlit, photosynthetic, but something deeper, more resilient, shaped by magnetic storms and eternal twilight. In fact, planets have been discovered orbiting pulsars. These dark systems challenge our assumptions about habitability. They suggest that life might not need warmth from light, only energy in any form, and time enough to adapt. And neutron stars offer time. Long after their pulses stop, long after their flares fade, they remain. For trillions of years, longer than the current age of the universe multiplied many times over, they will continue to exist. Even when all the stars have burned out, when galaxies have thinned and the night sky is no longer scattered with light, neutron stars will still drift through the dark. They will be among the last objects left, a gallery of collapsed memories circling in the cold. Eventually, they may cool further, fade completely, or decay through processes not yet fully understood. But even in that, they teach us. Even in fading, they inform. And what they leave behind is not only mass, but mystery. Neutron stars are one of the few places where we can test the edge of physical law, where general relativity meets quantum mechanics, where the strong nuclear force is not a theory but a structure, where gravity's pull is absolute but not yet complete. Unlike black holes, neutron stars have surfaces. We can see the results of matter colliding with them. We can observe how radiation escapes. We can study their spectra, measure their masses, and test how light bends around their edges. In them we find clues to the fundamental structure of everything. Because deep inside a neutron star, matter may not remain ordinary. At those pressures, new forms may emerge. Quark matter, where neutrons dissolve into their constituent quarks. Strange matter, a hypothetical substance more stable than anything in the periodic table. These exotic cores may hold secrets about the very nature of particles, how they behave when crushed together, how they interact when forced into proximity. We cannot recreate these conditions in any lab on Earth. We can only study the neutron stars themselves by listening to their pulses, watching their flares, and following the gentle curves of space around them. Even the silence of a neutron star is informative. When a once pulsing star stops emitting detectable beams, it is called a dead pulsar. But the star itself is not dead. It still exists. It still spins. It still has gravity and mass and magnetic fields. It simply no longer speaks in the way we can hear. But like all things in the cosmos, it may one day be awakened. A passing star, a burst of gas, a merging event. It may spin again or flare again, or collapse into something deeper. Perhaps even into a black hole. This transformation is rare, but possible. Neutron stars, especially those gaining mass through accretion, may one day cross the threshold where not even neutron degeneracy pressure can hold them up. And when that happens, they fall, not into flame, but into pure curvature, into invisibility. But before they vanish, they give us all they can: light, radiation, mass, time, gravity, even gold, especially gold. Every gold ring, every piece of jewelry, every ancient treasure dug from the earth, its atoms were born in a neutron star collision. Not in fire, but in fusion under pressure. When two neutron stars collide, they fling out jets of material rich in heavy elements: platinum, europium, lanthanides. These atoms drift, cool, gather. Some end up in meteorites, some in planets, some eventually in your hands. So when you hold gold, you hold the result of stars colliding with such force that time itself shook. You hold memory in metal form. To be human is to carry the echo of these stars, not just in your bones, but in your curiosity. You are drawn to them not only by science, but by story. The idea that something so small could be so massive, that something so dark could be so full of meaning, resonates with the quiet parts of us. Neutron stars do not scream, they do not glow with beauty, but they endure, they serve, they anchor, they teach, and in doing so they become more than remnants. They become reference points, fixed in motion, silent in song, gravitational in wisdom. So when you think of the cosmos, do not think only of the shining things. Think of the dense things, the hidden things, the ghosts of suns that continue to spin long after their light has gone. They are not gone. They are waiting, watching, whispering in pulses that cross the void and reach our telescopes, our instruments, our ears. And somewhere quietly we listen, and by listening we remember. We remember that mass has memory, that silence has rhythm, that even collapsed stars still hold the shape of the sky.